So now let's do the spherical wrist. But we're going to do something different here. Normally a spherical wrist is mounted on the end of your robot. So we're going to assume that joints 1, 2, and 3 we're controlling for position. So that's going to mean that these joints are going to be 4, 5, and 6. I'm going to draw in this value here. That's going to be my Z3. This axis coming out from here, that's my Z4. And then this axis going along here is my Z5. And I've attached a gripper at the very end of this. That's my Z6 frame right there. These are 3 rotational joints. So this is really, this is an RRR robot that I have here. And let's place, I'm going to place right over here. This is my X3 value here. So now we have to figure out, so that's my origin here. And so a right-handed frame I could draw in here as my Y3. So now we've got my Z4 is right here. That intersects at this point right here with my Z3. And so to be perpendicular to both of those, I could either have my X4 coming out this way, or I could have it come out this way. To match the book, I'm going to have it come out that way. So let's just erase this one over here. Now my Z3, my Z5 is coming out this way, and it's intersecting my Z4 at this point. So this point is going to be not only my O4, it's also going to be my O5 point there. And so I now need to figure out where my X should be. It's got to be perpendicular to both Z4 coming out this way and Z5 coming out this way. And so one thing that I could do is I could just make it come out right here, Z5. It's either that or come downwards, but it's kind of busy right there. So we're going to have that. So I've got to have it be perpendicular to both of that. So I can either have my X5 be here, or I could have it come down this way. It's busy down below, so I'm going to put it at the top for this drawing. And then I've got every other component I need. So now I need to measure my distances. So I've got a distance offset from here to here. This distance here is going to be my D4. Then I've got a distance here from my O5 to my O6. That is going to be my D6 value. Everything else is collinear, so there's going to be no radial values. So my radial values all be zeros. I've got this D4, and I've got a D6 and a 0 there. And then these are all my rotations. I should draw those in. So if I drop this guy down onto this plane, actually, so if I drop my X4 down onto this plane, that gives me this total angle that I've rotated there. That's going to be my theta 1. Now my angle from about my Z4 from here to here, that is going to be my theta 2. And then let's draw this X3 over here. Let's imagine that it's slightly rotated over there. That rotation that I have there is going to be, and again I've said this wrong, theta 5 and theta 6. This should be theta 4, 5, and 6. So theta 4 star, theta 5 star, and theta 6 star. Now my alpha values, this is how much I rotate around my X4 to go from, let's just write this temporarily. So I had my Z3 coming up here, and I want to rotate it towards my Z4 about this. So if I put my hand there, I could do a positive rotation all the way over here or a negative rotation the other. So I'm going to say a negative rotation. We'll have a negative 90 degrees there. Now my 5, I've got my Z5 coming along this way, and my Z4 coming along this way, and I've got my X towards the top, pointing out here. So I'm rotating around this axis by 90 degrees. And then you'll notice that my next two x-axes are aligned, so there's a 0 there. And so with all this, I can now build out my matrices. I've got my A4, which is equal to a C4, sine 4, 0, 0, 0, 0. I've got a negative 1 there because of that alpha value, and then a negative sine of theta 4, cosine of theta 4, 0, 0, and then a 0, 0, 0, 1. And this is depending on what value you set this. Since we actually put a D4 in there, we're going to put a D4 there. Note that usually you make D4 0. But for my drawing's sake, I've got that drawn in there so you can see it. So next we do our A5. A5 is going to be a C5, S5, 0. This one's a positive, 0, 0, 1. And we've got an S5 and a negative cosine 5, 0. We got 0, 0, 0, 1 through here. And then there is no radial or D offset. And we've got our A6 value. And here we've got our C6, our sine of theta 6. And our 0, 0, 0, 0, 1, 0, sine of 6, negative cosine of 6, 0, 0, and then 0, 0, 0, 1. And again, I've skipped this value here, which is my D6. And this is, just that final offset there. Again, to figure out what this is, if I want to know where my end effector is, that's T6 in frame 3. It's A4 times A5 times A6. And this matrix is ugly. Now there's a reason why I wrote this all out, and this matrix should look suspiciously familiar to you. I think it'll be more familiar if I switch some variable names. So check it out. This is this transformation matrix that we just made from 3 to 6. You can see we've got these C4, 5, 6. And right over here is the Euler ZYZ rotation. And you'll notice that we're able to match this rotation matrix 1 for 1 here, just substituting that phi is 4, theta 4, theta is theta 5, and psi is theta 6. And so you can see a 1-to-1 mapping for all these values through here. We've got our negative sine theta, c psi. And so this spherical wrist is exactly a rotation around the z-axis, a rotation around the world, around the original y, and then the current z. So this rotation is really a rotation around the current z, rotation around the current y, and then a rotation around the current z. So it is an Euler ZYZ matrix. And that's why we spent so much time in here. And so remember, we'll be able to do inverse kinematics because we can just solve for what this cosine, this theta 5 value is, and then use that value to figure out the rest of them. I hope you're about as excited as I am about that. So let's remind ourselves of the cylindrical robot. Our origin right here, and we take a step up here. This is our D1. Then we've got our variable extension here, D2 star. Then another extension over here, which is D3 star. Z0 is aligned with Z1, but Z2 is not. And so if you rotate around this axis, you can see that we rotated either a positive 270 degrees or a negative 90 degrees is equal to our alpha 2. All the other axes are aligned. And so 1, 2, 3, we've got 0, 0, 0 for radial offsets, and we've got a 0, negative 90 degrees, 0, and then our D1 and our D2 star and our D3 star, and then our first variable, if we drop our x down here, maybe we've done some rotation, theta 1 star. So we've got theta 1 star and then 0, 0. So this is our cylindrical robot. So what we're going to do now with this lovely cylindrical robot that we have is we're going to bolt that spherical wrist right on the end. And so these are the first 3 variables that we have, and then these next 4, 5, and 6. And so we can concatenate those 2 tables and make one monster table out of them. So all we do is we copy those values in here. I've got zeros for all of my radial values. I've got my D1 here, my D2 is here, my D3 is all the way through here, and then I've got a D6 here. So I can write those in here. D1, D2 is my star value, D3 is a star value, and then I've got a 0, 0, and a D6 here. My theta values are my other values that are my rotational joints. So that's theta 1 star for this one. We've got a 0 and a 0. And then the rest of these, theta 4 star, theta 5 star, theta 6 star. Then my alpha values, I've got a 0, a negative 90 degrees that we just saw, a 0. Again, we've got a negative 90 degrees and a 90 degrees and a 0. And that gives me my entire rotation. Now I could go ahead and I could make my A1, A2 all the way out to A6, multiply those together, and I get my transform of what is 6 in frame 0. I'm just going to show the answer for that one. First off, let's remind ourselves what that cylindrical robot alone looked like. So I grab right here, I'm going to build this out. This is my transformation. It wasn't too complicated. I can rotate that ending point around, and I can retract or extend D2 and D3. Now let's look at what happens when I combine the spherical robot and the spherical wrist. So I have a much larger DH frame here. When I multiply this out, this term actually becomes quite complicated. That is a whole term right there. But there's a lot going on in this one. So it quickly becomes complicated as we multiply these out. And here you can see our spherical wrist is bolted on the end of our cylindrical robot. So I can rotate that robot around, and then I can move up, and I can extend my arm out to grab the things that I want to grab. And I can put that arm at whatever orientation I want. I can rotate this. Actually, I'm going to put an offset in this first. And now when I rotate the 4th joint, you can see I can lift that up and spin that around. And then I can finally rotate my gripper at the end how I want. And then I could go grab something. So now let's talk about a robot called the Stanford Manipulator. 1969. It's an oldie. And so we'll start off by just drawing in our rotation axes. So you've got our Z0 right there. I've got my Z1 here. Z2, Z3, Z4, Z5. So next, let's draw in our non-zero values that we have offsets on. And so this distance right here, this is D1. It's just a constant value. It's what's built in there. And we've got this value here. This is also along the z-axis, so this is D2. And then here we've got our variable value, and we're going to say that this entire distance all the way up to the wrist center point here, that is D3. And then finally we've got another distance here, that is a variable D3. And then over here we've got our D6 distance, and that is not a variable. We've only got one prismatic joint in here. So next we need to draw in our x-axes. So coming right out here, that's going to be my x0. So if I drop this down here, that angle right there is theta 1 star, my first revolution there. I've got an intersection of this Z1 and Z2. I've got an intersection right here of the Z1 and Z0. So I'm going to bring my x1 out here, and then if I take that value here, this will be my x2. So the angle that I rotate between those two is going to be my theta 2 star. And then this quantity up here, that is my my spherical wrist. So that is my x4 sticking right out there. So I'm going to put together I'm going to say that this is also my origin for 0, 3, 4, and 5. So this one will be my x3, and this rotation, actually the rotation all the way around here, that is going to be my theta 4 star. And so I've got my typical, this is my spherical wrist right up here. So I can write in everything in now. So I've got links 1, 2, 3, 4, 5, and 6. My radial offsets that I have, I've got no radial, so it's zeros all the way through here. My D values, I do have these D values. I've got my D1. I've got my D2, my D3 star, and my D6. Then I've got my theta 1 star, theta 2 star, 0, theta 3 star, theta 4 star, theta 5 star. I am going to have some alphas. My first alpha, if I need a twist about my Z1 to go from Z0 to Z1. So that's a negative 90 degrees. The next rotation that I do is about my x2 axis. So I'm going to rotate from here to Z2. That'll be in 90 degrees. Then my next axis here is a line, so I get a 0. And then I've got my typical spherical wrist here. And that gives me my entire transformation. Again, when I multiply that out, it's going to be complicated. So I'm going to just go to Mathematica to show that. Let's look at that Stanford Manipulator. I'm going to build this out here and run it. So here is our DH frame that we had before. When we multiply this all out, I'm going to be looking at the total transformation from 0 to frame 6. And that is this term. This is the first column right here. All right, here is our second column. Here's our third column. And here is our fourth column, even after simplification. It's not all that simple. Let's take a look at that robot. So here's our robot. And we can tip off axis, rotate theta 1, there, and then we've got our spherical wrist. So let's do the forward kinematics for the SCARA robot. And so we've been kind enough to already draw in the axes, so all we have to do is draw in here some of the distances. So this distance that we're moving over here, this is along the x1 from the z0 to the z1. That's going to be my r1, whereas this distance right here, that's the distance that I've moved along my z0 axis. So that is going to be d1. If I dropped this value down here, this angle here is theta 1 star, because it can change. And then this angle from x1 to x2, that's going to be my theta 2. This distance that we go from the z1 axis to the z2 axis, that's r2. And then this distance that I extend downwards, we can call this distance d3 here. But if we do that, then we have to talk about the rest of the distance that we go down. So the rest of the distance that we go down into this frame here, we can call that one d4. So now I've got d4 coming there. I've got all my distances that I need. And so now I can start filling this in. I've got my r1 here, and my r2 there, 0 and 0. My d values, I've got a d1 there, a 0, then a d2 star. That's my prismatic joint, and then a d3. And I've said that wrong. This is the d3, and this is a d4. Okay, and now on my theta 1, I've got a theta 1 star, theta 2 star, 0, and a theta 4 star, my final revolution. Now I'm missing my alpha values, so let's change to blue and see what happens. So I've got my z1 is parallel with my z0, so there's a 0 there. However, my z2 is pointed in exactly the opposite direction, so I've got a pi there, or 180 degrees. And then my next two axes are aligned, so 0 and 0. So I could take this, and I could say that my final transformation, what is 4 in frame 0? Well, that's going to be A1, A2, A3, A4. This lecture is getting a little bit long, so I'm just going to write these in. So that is theta 1 plus theta 2 minus theta 4, and that's because theta 4 is upside down compared to 1 and 2. So we're going to subtract that off. Sine of 1 and 2 minus 4. Sine of 1 and 2 minus 4. And here we have a negative cosine of 1 and 2 minus 4. And a 0 and a 0. 0, 0, 1. And we have a C1R1 plus C12 R2. And we have a sine 1 R1 plus sine 12 R2. And then finally, our total depth that we follow, well, first we go D1 up, and then we go down D4, and then down D3 star. We've got a 1 here, 0, 0, 0, to complete our homogeneous transformation. And so you can see that we can't access everything. In fact, what we can do is we can access and we can make our x-axis point in any direction in the plane, the xy plane, but we can't change our z-axis. We can find an arbitrary z position, and then we can go to arbitrary x's and y's as long as those happen to be within our workspace. So let's take a look at what that SCARA robot looks like. So again, I am going to add my DH parameters here, and then I say let's run with that example input, and then I'll run forward kinematics and show you. Actually, let's add and also show this fourth one. So we build it out. There's our DH parameters. Here is A1, 2, 3, and 4. When we multiply those together, this is relatively simple. the form that we get. Let's take a look at our robot. Our theta 2 pivots along that point. And so theta 1 is this angle here. So theta 2 is this angle here. We can rotate that around. Come backwards. Remember, the whole point is that we can place this in effector wherever we want, and then we can achieve the desired orientation of it. And then, this is for picking and placing. So let's do a side view and show it actually doing that placement.